I should also explain to all of you that this Nobel thing has interesting challenges associated with it. Firstly, you don't really know how to refer to yourself. So some of us say, oh, when we went to Stockholm, or the Swedish medal. Because of my strong affinity with computer science, I say I'm now NP complete, which makes everything exponentially difficult. And I think that's probably most accurate. I should say that giving an author dinner speech is definitely not my thing. And as a result, I dress up in a way that I don't normally dress. And this is not actually me speaking, it's some actor that I hired. So he's going to say things that have no meaning and so on. So I'm going to go through my slides. Apparently I'm not allowed to move because I've got to be next to the microphone in the camera. And I'm going to look somewhat frozen, but don't worry about that. So I'm going to probably skip sections 1 and 2 because a lot of this has been said before by Ilan. I'll probably show some of the movies, then say something more about current work on very large systems, applications to human health, and some general thoughts. So I was very, very lucky, as Ilan said, that I was sort of a teenager at the right time. And in Hebrew, I think a lot of things in life are just luck. No one likes to say that. Let's say chance. But in Hebrew, the word for luck is mazal. And you can take each of those letters and say it's place, time, and whether you speak out or don't. And I think in some ways, a lot of things in life are given by that. So I was very lucky that I was a teenager in the 50s. And this was a time when biology was changing dramatically. And there were 4 individuals particularly who had a very large indirect role on my existence. So one was Linus Pauling, who sort of was the ultimate chemist, showed the world that modeling and thinking could be applied to really complicated systems. Then there was Francis Crick, and with Watson in 1953 they published a model of DNA which had incredibly far-reaching implications and was based on positions of 30 atoms per nucleotide. So basically, a small number of atoms led to a complete explanation of how biology works. A person who probably had a bigger effect on me than even Francis Crick was John Kendrew. John Kendrew also determined structure. He determined the first crystal structure of a protein. It was published in Scientific American in 1961, and that was a premier place to publish because things were in color. Nature and Science were black and white. If you had a complicated system, you really wanted to get it into Scientific American, which is what Kendrew did. Now, as in 1961 I was 14 years old, I was subscribed to Scientific American. So this beautiful model of myoglobin lands on my doorstep or whatever in South Africa. And I suddenly realized that biology is governed by things that are very highly organized in space and in time. And for me, that was a complete mind-blowing revelation. Just to add a little bit of social science, in some senses, the real hero, I think, of molecular biology is Max Perutz. He's somebody who is not nearly as flashy as Francis Crick or John Kendrew, but basically John Kendrew used Max Perutz's methods to solve myoglobin. Max could not solve hemoglobin, it was too difficult. Max was also Francis Crick's PhD supervisor, and Crick actually solved the structure of DNA while he was a PhD student for Perutz. Now, you've all heard of Watson and Crick, but it's not Watson, Crick, and Perutz. Today, that's exactly what would happen. Perutz did not put his name on Crick's work, and Crick's paper is just stuck into a folder at the back of his thesis. So in those days, there was a massive attempt to make people independent as much as possible. So to move on to how I got into this, and again, Ilan has somewhat usurped my slides, and I think it's fitting because I've been using these slides for far too long. Basically, Kendrew was really important to me, and I'm going to show you something which no one has seen. So basically, I left South Africa when I was 16 in 1963, came to England, saw television for the first time, became totally addicted to television, and fortunately, Kendrew had a program on television called The Thread of Life that aired in January 1964, and I watched this among lots of other things. This was basically introduction to molecular biology. Now, it turns out that recently in Israel they made a documentary film about the various Nobelists, and the documentary filmmaker had really good archivists who actually managed to track down this series by Kendrew, which everyone had said had been lost. So here you're going to see it. This is now. The sound is not very good. So this is a program which I think it's the only surviving episode. I think I'm violating all sorts of laws by showing it to you right now. This is meant to be for private use only, and you can see there's a date stamp, and I think I need to pay $55 a frame to show it to you. That's 55 times 24 per second. But here's Kendrew.
In the last lecture, we were talking about proteins as long chain molecules, long strings of amino acids, and we were talking about them mostly as if they were one-dimensional objects, but towards the end, we were saying that this was an inadequate description, that we had to go into 3 dimensions, think of them as solid things, if we were going to understand how they worked.
It carries on, but I think that's a really good justification for 3D sig. I mean, 3 dimensions really matters, and Kendrew has said that. Here is Lifton and myself. Again, just to remind everybody, biomolecules are detailed. We don't need this, but this is something which I think we still, I mean, it's pretty amazing that all life depends on where atoms actually are, and it's nothing magical. I mean, it's very complicated, it's very involved, but it's not magical. Again, just showing you myoglobin from Kendrew, and next to it lysozyme, which came 5 years later. Phillips actually managed to get the cover of Scientific American, which was the absolute ultimate place to be. We've already talked about this and this. I'm just going to say something which Ilan didn't say, that if you have the potential energy, you can get everything. Physics is lazy. You can do energy minimization. If it works in one dimension, it works in many dimensions. You just drop down to the nearest minimum. You can do normal mode vibrations where you vibrate about a minimum. There it is in one dimension, and now in 2. You can do molecular dynamics, which is a kind of minimization, but now you just keep kinetic energy, which allows you to go over barriers, again in 2 dimensions. And finally, we have Multiscale, which I'm not going to get into, although in some senses it's the most interesting of the methods. It's the simplest of the methods. It's also the only method that was actually classified. If you look at the authors, the key paper on Multiscale has as its authors Metropolis, Rosenbluth, and Teller. That's Edward Teller, the father of the hydrogen bomb. And it was basically a classified method that was used to design hydrogen bombs in, I guess, the late 40s, and was only published in 55. So an equation that is essentially this, except with probability, is actually super classified. Okay. Ilan already mentioned that we built models, we did minimization. This is with Lifton, my first paper. I then basically finished my year in Israel. This was a year where I went to Israel before doing my PhD, not because I really wanted to. This is 1967. Israel has just won the 6 Days War. Many Jewish people went to Israel for patriotic reasons. I went to Israel because John Kendrew told me that if I don't go to Israel to work with Lifton, he won't take me as a PhD student. And then he made it a little bit sweeter he actually got me a postdoctoral fellowship to go to Israel before I did my doctorate. And this was just simply lots of money. So, world is strange. Anyway, I went to England. I was married by this time. We had 2 children. I did my PhD, came back to Israel. When I worked with Varshil on multiscale modeling. Now, towards the end of the talk, I'll say a little bit more about multiscale, because it was actually just a trick that was used by the folks in Sweden. Okay. So Einstein is said to have said, everything should be as simple as it can be, but not simpler. And that's sort of obvious. Turns out, at least according to quote investigator, that Einstein never actually said it. It was said by Roger Sessions, a newspaper guy, and he just wanted it to sound fancy. And apparently there is a term for, I forget what it is, but there's actually a word on the internet now where somebody quotes what somebody else has said, and the quote gets attributed to the more famous person. So it's like quote squatting or something like that. I need to look at the term. In any case, this is really, really important when it comes to simulation. Let's say you want to do a calculation, and you don't make it simple enough, and with the current methods of calculation, you can get 1 step a year, i.e. you can get nothing. So that isn't going to help you. On the other hand, you could choose a model that is so simple that it isn't even worth doing the calculation. So somewhere in between worthless and infinitely time-consuming is a position, a sweet spot, that's really important. This is a little bit like the story of the physicist who's asked to consider a cow, and he says, well, let's take a spherical cow. Now, that's obviously stupid, but if you were to talk to a molecular analysis and say, let's take a cow, and he said, okay, let's take 10 to the 25 atoms and simulate it, that would be probably equally stupid. And the right answer might be that a cow is represented quite well with 100 spheres, or 1,000 spheres, or something like that. So simplicity, getting the right level of simplicity is very important. Arya Varshil and I did 2 kinds of things. Coarse-grained models, where we basically simplified a polypeptide chain by throwing away most of the atoms to allow you to fold up on computers circa 1973 or 74. This was folding that was done not by dynamics, but by doing energy minimization to get into a local minimum. And once you got into a local minimum, we calculated the normal modes and then jumped out along low energy degrees of freedom. It's a way of doing normal mode thermalization. Something else we did at the same time was combining quantum and classical models for catalysis. This was based on David Phillips's work. He had shown in the crystal structure of lysozyme and a tetranag substrate, he thought that the enzyme actually worked by physically stressing the substrate, essentially trying to bend the substrate and therefore making it break. I had tried to do this in my thesis, and it turns out that lysozyme is just too soft to do it. The analogy, which is not a very nice analogy, is if you want to break somebody's back on a rack, you better make the rack out of wood or steel and not out of a really soft sponge rubber, because it's just not going to help. It's not going to be able to do it. And proteins are too soft to break substrates. It's got to be done somehow else. Phillips had speculated, as had others, that it was electrostatics. Here's an aspartic acid or glutamic acid that's marked as having negative charges. So together with Arya Varshil, we teamed up and introduced quantum mechanics into the system. So now you've taken an atom and replaced it by 10 electrons. And this was, the difficult thing here was how you couple the quantum part of the calculation to the classical part. This was definitely Arya's doing. We also had to bring into play an explicit solvent model. And this was actually a very difficult thing to do because you had to make everything balanced properly. And, you know, it was, but I think in the end, we got it to work. And I think more importantly, the basic protocol became a generally accepted one. So now I think we've sort of passed the golden age of computational biology. We're up to about 75, 76, 77. At this point, the word spreads. A very important player who is not well known to our community was Anusha Raman. He actually died at the age of 60, which is kind of young. He had, in the 50s, done very pioneering molecular dynamic simulations of argon. 64 argon molecules, or argon atoms in a box, behave just like liquid argon. He then went on and with Stillinger in the late 60s, did a series of papers showing that liquid water could be simulated and give you very interesting properties. So essentially, using the force field that Lifson and Varshall had developed with my programs and these methods, it was possible to do the first simulation of protein dynamics. This was done by Martin Karplus, who shared the prize with us, Bruce Gallen, who sort of left science and became a professional clarinetist, and Andy McCammon, who is still very much involved. They took the small protein bovine pancreatic tryptophan inhibitor. This protein is famous because it was half the size of all the other proteins that were known for the first 10 years of its existence. So all proteins were 125 amino acids, and BPTI was 60 or 58. So you can actually see in the calculation that the molecule has moved. This is the structure from their Nature paper at time 0. This is the structure after 3.2 picoseconds, and the end has moved. But it's clear that it's really hard to see movement from still pictures. We made a movie, and I've left out all the acknowledgements, but it was too short. Basically, this movie was very difficult to make. Every frame was 1 day frame, 34 frames, 25 frames a second, 1 day on a big machine at NIH. Just the algorithm for drawing shaded spheres, which is completely trivial nowadays, was sufficiently difficult that Bacon, who developed it, was one of the founders of Pixar. So there were good days in those days. Anyway, the motion is odd, to say the least. And I don't think I actually ever liked this music, so I guess that might have been a false like, but we need to audit my Facebook. In any case, the motion here is interesting. Basically, things are moving around, not really going anywhere, but this is actually what it looks like. I do remember I saw the first 20 seconds of this movie when I was at the Salk Institute with Francis Crick in 1978, and we were blown away. We just could not believe what this looked like. Nowadays, it's very old hat. Interesting that the water molecule, which is inside the protein, there were 4 water molecules, gets expelled, reminding us that this whole calculation was done in vacuum, and all calculations for the first 10 years of protein dynamics were actually done in vacuum, which is odd because the background for simulations had come from Raman's work on looking at liquids. So I then, during a period I was in Israel, devoted about 10 years to try to find out how to do simulations of a protein in liquid water. This was done together with Ruth Sharon, a technician at the Weizmann Institute, and in 1986 we managed to get 100, maybe 200 hours of Cray XMP at the San Diego Supercomputer Center. That actually cost the NSF $200,000 of 1986 dollars. So that's probably like $1 million today. It allowed us to do 200 picoseconds of BPTI that you could do on a laptop in about half an hour today. And the upshot was that if you did the simulation in water, green line, it remained much closer to the X-ray structure than doing the simulation in vacuum. These are various other points that were done by other people, either in vacuum, and this is our point in water. Basically, water is essential for keeping the protein well behaved, and nowadays almost all simulations of proteins are done in explicit water. Here's an example of a water simulation done with Valerie Daggett of alpha helix unfolding. Valerie was my first postdoc. Here it is. I should say that in my career, I had a lot of collaborations, but I didn't have a group until my eldest son was 18. And I think I was just scared to actually try to direct people without knowing how to handle them. I don't, if I still know. In any case, here is an alpha helix. It is at room temperature, and it's not unfolding, it's moving around. There is some motion at the end here. Room temperature, 5 degrees Kelvin, centigrade. Hydrogen bonds are breaking. The waters are always here, but we leave them out sometimes. So just now we're going to go to high temperature. This particular movie was ridiculously high temperature. It was 200 degrees centigrade, and in no time the alpha helix melts. This again is an important test because if your calculation doesn't melt the alpha helix, you're doing something wrong. These kinds of commonsensical tests are very important. This movie was very significant because I actually made it for a lecture that I gave to Linus Pauling in 1990. And it was sort of nice to show Pauling the alpha helix moving. More finally, the film was made by filming with a Bolex 60mm camera off a silicon graphics screen. And I didn't really line it up very well, as you can see. You never really think that these movies are going to be around for that long. At about the same time, my first PhD student, Marie Hirschberg, who was a student at the Weizmann Institute and then came to Stanford with me, did exactly the same kind of treatment for DNA. It was much, much more difficult. Basically, DNA in vacuum just goes completely crazy. This is a 6 angstrom RMS deviation. In water, if you do it correctly, it behaves well. A lot of people now say that you have to do it correctly by having air-belt boundary conditions and things like that. That actually isn't true. You can do it with short-range cutoffs if you do it properly. And here's the example of a movie of DNA dynamics. See, here we have 12 base pairs of DNA in a big box of waters. You need to have lots of sodiums to counteract the negative charge on the phosphates. These are sodium counterions, 2 for every phosphate. And basically, not a lot is happening. If you look very carefully, the end of the helix is breaking. I think there's a base pair over here that breaks temporarily and reforms. But the structure is basically not doing very much. In order to emphasize what's going on, actually show you exactly the same sequence going faster and faster, because the eye picks up things at the right speed, but even at this high speed, you can see just the same things are happening. Now you can see it again in skeletal. This base pair is going to break. There it breaks. I think there's a base pair here that breaks, but basically that's it. Okay. So now moving on to the present time. So basically, we're interested in methods for multiscale dynamics of very large structures. And here we're just going to see 3 examples of what we mean by large structures. So the key thing in all of this work is to reduce degrees of freedom. Now that sounds obvious, except that typically in a Cartesian coordinate molecular dynamic simulation, every atom has 3 degrees of freedom. And that is not necessarily the right way to do things. If I wanted to model my arm, so what is the best way to model my arm? To think about the 10 to the 24 atoms in my arm, or to think about 20 degrees of freedom, twisting, bending, etc. And I think that reducing degrees of freedom is critical, and it's going to be one of the tricks in multiscale dynamics of large systems. So here's an example of work done by Shui Huang, an ex-postdoc and his ex-PhD student Daniel Silva, on Markov state dynamics of RNA polymerase. Markov state dynamics is an interesting and very intuitive idea. Essentially, you set up a multidimensional energy surface for your system. So here's an example of what it was based on. I think it actually came from robotics. There were things called probabilistic roadmaps, where in order to plan how a robotic arm would move around without bumping into things, basically you just simply created a grid of possible positions and would see that in these positions things are good, and in these positions things are bad, and then you can plan a path by moving from good positions to other good positions. So you can go from here to here by just joining up all of these feasible paths. So Markov state models are exactly the same. You run a lot of simulations in parallel, and each simulation maps out a different part of the conformational space. You need to find a way to make the system explore the space. We did this. Here's an example of work from Vijay Panda, where essentially during folding you again get multiple states. Each of these states has a certain energy, a transition, and from this you can then simulate the dynamics by just jumping stochastically between states. Here's an example of the 1,000 states of RNA polymerase. What we did is we used morphing to go from a state over here to a state over here along this path. And then from every one of these points, we ran a few tens of nanoseconds of simulation. It was a very big calculation, required a supercomputer in Hong Kong for about 6 months. And once you've done that, you can find that there are all these different local minima and transitions between them. And then you can start just joining things up to make the transition. The good thing about this is it forces you to look at many, many states and actually look at the energy surface of the system. Now, here's a movie that shows this much more clearly. It's a large system, almost 500,000 atoms. Now it's going to start moving. Again, this was a movie made by Shui Huang and Daniel Silva. And these movements are not molecular dynamics movements, these are stochastic jumps between states. The time scale is determined by the barriers between the states. So RNA polymerase is a quite large structure. It's about 3,500 amino acids. It basically copies the blue strand of DNA into a red strand of RNA. So it basically transcribes DNA into RNA, and the key step in the reaction is to see how this nucleotide, which is the next one along, is going to jump from here to over here, wait here, so an incoming nucleotide can bound. This is the cheat chart. When this goes down, it starts to move, and now it moves all the way. And now I stop it, so now this is perfectly posed for an incoming nucleotide to base pair here and then catalyze the next step in the reaction. So RNA polymerase is a very, very simple system. Yet you've got this very large machine dealing with it. Now the ultimate large system that we have to deal with is the ribosome. Here is a very simple calculation on the ribosome. It's not a molecular dynamics simulation, it's the normal modes, done by ex-postdocs Janelle Bray and Junji Chang. Janelle is actually at LinkedIn, and Junji is an assistant professor at Texas A&M. So these are normal modes. These were calculated by a program that I wrote. They ran on my laptop in about 4 hours. This is to get all the normal modes of the entire ribosome for a single point for each nucleotide or amino acid. This is about 10,000 particles, and this is 200,000 particles. Every single atom is here, and you see lots of kinds of interesting motion. We're now investigating the ribosome. It's become a major project of ours, and some of these motions are actually seen if you compare different states of the system as observed by crystallography. Another kind of method is to use what we call natural move Monte Carlo, developed by Peter Minari, who's in the audience. Peter was a postdoc and is now tenure-track faculty at Oxford University in England. And Peter had this wonderful idea of a Monte Carlo method that made any move you liked. It didn't have to change a Cartesian coordinate or change a torsion angle. It could do whatever you thought was a good move, anything you wanted to do. Now, when you make a move like that, you might break local geometry. If I said I wanted to move my elbow up, it's a special move, but if I just pulled the elbow up, I would break things. Now, Peter's idea was that you would fix the errors very quickly before you would accept the move. And this allowed you to actually get very large moves. Here's an example of applying to DNA. So here the move is for a single, you actually move the entire base pair. When you move a base pair, because of the double-stranded nature, you break bonds. Those bonds are fixed, and then you can make this hierarchical and essentially very quickly sample RNA conformations in a way that is much greater than you'd normally get by regular Monte Carlo. This work was done with Adeline Sim, at that time a PhD student and now a postdoc in Singapore. And together they also showed that you could actually even do things like take very large RNA structures and actually sample their flexibility by this method. Peter also used his method to look at nucleosome positioning from first principles and showed that if you took genome length sequences, about 20 kilobases of yeast DNA, it was mouse, I forget that. You could actually predict whether nucleosomes are going to bind by just ab initio energy calculations. Basically, in regions where the DNA bends easily, the nucleosomes bind, and it gives you a very simple idea, and this can be affected by epigenetic marking of the DNA. By methylating Cs in 5 positions, you very dramatically alter the flexibility of DNA. So again, this is a different approach to very large systems. Okay. So now I'm going to say something about applications to human health. I'm at a medical school. I do basic science. At a medical school in the USA, you have to basically find your salary essentially from a grant. People who teach get 3/4 of their salary from the institution. If you're in a medical school, you get about 1/4. So it's clear that teaching is worth about half a salary, and we're meant to find the rest of our salary from grants. Now this means that if you get an endowed chair, it's a big deal because suddenly your salary is paid for. at Stanford about 5 years ago, got an endowed chair. Now, the way the endowed chairs are given out is people endow a chair, say, for cancer research or for cardiology or something like that. But the dean doesn't sort of say, oh, you're working in cancer research, you're going to get I have the Cahill chair for cancer research. So I got this and was very embarrassed because I wasn't working on cancer. And immediately thought I was going to now spend the rest of my life working on cancer research. So I had to go and meet the family, talk about what I wanted to do, and was going to promise them, I would not touch anything that wasn't cancer-related till I die. And then I suddenly realized this is a very big thing to say. Rather than promise the future, repurpose the past. So basically, I was able to do an application in human health that involved a repurposed success story. This actually involves Arthur Lesk and Cyrus Chothia. Pretty sure Arthur's in the audience. But basically, in the early 80s, Arthur introduced me to antibody modeling. At that time, the problem was how do antibodies get such great diversity? Cyrus Chothia and Arthur Lesk have written some amazing papers about canonical models for antibodies and so on. I decided to take an easy way out and to write a computer program that, given any antibody sequence, would build a model. And basically, there were 6 hypervariable loops, and depending on the loop conformations, you get different binding sites. Now, this ended up being something which led to papers. Here are papers involving Arthur and Cyrus and myself and a lot of experimentalists. 2 papers that at least were published in good places. There were other papers basically predicting the structure of antibody loops before crystallographers solved them and seeing that by and large the disagreement wasn't too bad. By the mid-80s, I was already sort of bored with this. It took a while to get the papers published, but I had this program. I moved to Stanford in 1987, and as part of my sort of coming to Stanford, I was asked to join a startup company that had been founded by Carrie Queen and Lawrence Korn, called Protein Design Labs. It started out with a very broad focus on protein engineering. Remember, we had cloned, we could express any protein we wanted, we knew how to clone DNA. Protein engineering seemed to be the brave new frontier. Now, I think in many ways the greatest achievement of Protein Design Lab was getting the SAB to meet. They had a pretty amazing SAB, Roger Kornberg, Levitt Stryer, Lee Hood, Stan Felker, and myself, and we met every 3 weeks, at least for 2 years. Nowadays you couldn't get these people in the same continent, so it was pretty amazing. Anyway, after a while they decided that instead of just doing broad focus protein engineering, they would actually look more carefully at antibody engineering. And they wrote a paper in 1989, a humanized antibody that binds the interleukin-2 receptor. Queen is the first author, and I'm one of the authors here, because I wrote the computer program that I had anyway that allowed them to make a model of the antibody. Now, why did they do this? So first let me show you the model. This is actually from the paper. And what you basically see is that these are the loops that come from the mouse. So you take the interleukin-2, inject it into a mouse. The mouse creates antibodies against it. Take the antibodies, sequence them, and then take the sequences of the loop amino acids and put them into a human framework, so the resulting entire antibody is human. It will not cause the human immune system to get upset. This is what immunization is all about. Now, the basic idea for doing this was put forward by Greg Winter and colleagues at MRC in the early 80s, and Greg's idea was to simply take a human framework, shown here in white, stick in the mouse loops, and now you have a humanized antibody. Now that's a good thing to do, but Queen realized that you had to go a bit further. And because we were dealing with patents, going a bit further means it's a completely new ballgame. So Queen said you have to basically take the antibody CDR residues, the loops from the mouse, take a human framework, and then make some changes in this border region. And again, if you look at the picture, it makes perfect sense, because these amino acids actually touch these amino acids. And sometimes there'll be a contact between this and this that are critical. Queen also said one other thing that was particularly interesting. There are many, many different human antibodies. And some human antibodies are just very much like mouse antibodies. So a good trick is to choose a framework that is very close to the mouse framework, and then nature does it for you. In any case, they did this. Because it was a company, everything was patented, and they got pretty good patent attorneys. They got a lot of money. It became big biotech and big money. Basically what happened was they managed to persuade Genentech, which later became a subsidiary of Roche, to purchase a license to this patent. They had shown in a very simple test that if you did what Winter said, the humanization was not nearly as effective as doing what Queen said. Now, that isn't surprising because Queen has more degrees of freedom. But patents don't normalize by entropy. This has more entropy than this because you can do more, so it's going to be always more flexible. Anyway, so this thing worked. They managed to get things in, and the company sort of did well and didn't do well. It actually reached a market cap of $7 billion for a very brief time in 2001 before essentially disappearing. The company right now simply consists of 7 employees living in the Nevada side of Lake Tahoe, which means they avoid California's sales tax. And what are they doing? They're basically collecting royalties. And right now, the royalties, at least, this is all past tense, because in December 2014, the 25 years since 89 had passed, the patents expired. But 2 years before then, they were bringing in almost $500 million of royalties. Because these drugs, I don't know whether their royalty rate was 2% or 3%, but these drugs had a huge market valuation. And very sadly, I guess I don't want people to know what these names are, because it's not a good thing. But I read somewhere that these drugs extend your life by about 6 weeks for like $500,000. So I know there's a lot of ethical issues, but the important thing for me was this meant that I'd already done cancer research, could get the chair, could tell the story to the family, and carrying on doing what I wanted to do. Okay. So just some final thoughts. So there's absolutely no doubt that the whole field of computational biology has been pushed forward by technology. And one of the strange things is that after you kind of hear up the Nobel Prize, you spend the first week doing nothing but giving interviews and saying silly things. And you suddenly realize that one of the really nice things about being a scientist is that you're expected to think. Actors, I guess they can say their lines and they can recount the same stories, but they're not really thinking. So at one point, I got a request, I think, from the San Jose Mercury News, would I please tell them how much computers had changed since 1967? And the obvious answer would have been Moore's Law, Wikipedia, leave me alone. But I said, wow, I've got a chance to think. So I sat down and made a table where I said 67, 2013, and I looked at the computers that I used back then, what they cost in today's dollars, and my laptop today. I ran exactly the same calculation that I ran in 1968 on my laptop. It was 10,000 times faster. The memory on my laptop is at least 10,000 times more than the memory back then. I think, in fact, the memory of that machine, I think, was 2 megabytes. It had a 36-bit word, so it's complicated and not easy. But I remember 200K words was a big calculation. And finally, I think a laptop is at least 10,000 times smaller than the hall that housed the computer. Now, it's interesting why all these numbers are approximately 10,000, and maybe that's because I sort of fixed them that way, but I still think it's interesting that each of these things has been about 4 orders of magnitude. And then you make the obvious joke to Sweden, if cars were like computers, then a new Volvo would cost $3, would have a top speed of probably 2 million kilometers an hour, would carry 15 adults in comfort, and would park in a shoebox. Now, that's funny, but it's actually true. I mean, about computers, every one of those factors is true. And this means that the power we have is unimaginably large. And more importantly, looking, say, 50 years into the future, I think almost all of us say we're certainly going to get bigger factors than this, from new technologies, teaming up machines, very high-level parallelism, quantum computers. I mean, 40 years ago, we had no idea that any of this would happen. Now it seems much more obvious. Okay. What next? So I guess one thing that sort of bothers me, well, let's just look at this carefully. So in the last 60 years of simulation, we've got at least more like 1 billion times more computer time. Systems have, now what have we done with that computer time? We could do 3 things. We could look at bigger systems, we could look at them for longer time, and we could use better energy functions. Well, what we've done is we've looked at bigger systems, we've looked at them for much longer times, but the energy functions have become simpler. Raman and Sillinger had lone pairs on their waters. Nobody has lone pairs on their waters anymore. So it's actually quite disappointing that we seem to be very happy doing things in the old way. I don't think that's good enough. I think in the future we're going to have to move to get away from what I call the dead physicist energy function and go to something more modern, probably parameterized interactions on quantum mechanics. I tried to get this funded by NIH, but they didn't want any of it. So it's been done by companies. Algodyne was a company, actually, that Carrie Queen founded in Moscow. I was a scientific advisory board. And Interact is a new company that involves Roger Kornberg and myself with funding from somebody else. And we're trying basically to develop energy functions that will be accurate enough to calculate the binding of drugs. And the reason is that you might be able to use empirical energy functions for proteins and for nucleic acids, but when it comes to drug binding, i.e. new molecules, these molecules are going to work by basically using loopholes in the energy function, highly polarizable atoms next to very strong charges, etc. So we need to have a really accurate representation. Fortunately, in the intervening time, quantum calculations have become really good. So you can take 2 simple molecules, 2 water molecules, and in any position you put them, you can actually get a good value for the energy. I currently have a pretty small group. I've always had a group, I guess, whose size went from 4 or 5 to 10. And I think it's sort of interesting because although the group is small, we're working on a lot of different things. I used to be very circumspect about my lack of focus, as in, NIH grant review comes back saying there's no focus in this grant. I can now get away with lack of focus. And Andrea is working on comparing whole genomes. I'll say a bit about that in my talk on Sunday. And Jana is working on cryo-EM membrane proteins. Ivan is working on density functional theory quantum mechanics and the X-ray first problem. And Nick is working on ribosome dynamics and chaperoning CCT. Okay. So I should mention, as Ilan said, that family support is very important. And actually my wife was going to come, but I think if she'd been here when you were talking like that, I would have paid for that for a very long time to come. So I'm actually glad she didn't come for other reasons. But in any case, it's been really important having family support. Here's a picture of my mother 2 years ago. She is now 100, and I've got to go back via London to fix her computer because she had a disk crash and so on. Whatever. I want her to stop using a Windows machine and use a Macintosh, but that might be difficult. People have said that she's not that young anymore. My wife, Rena, this is at the Jewish festival of Purim. She doesn't have a skin disease. She's got a flower on her face. And at that time, my eldest granddaughter, we've been very lucky. And here people say, I'm really bragging. We actually now have 6 grandchildren. And that is in some ways a much more satisfying achievement. The old saying, and I'm sure you've all heard it, but it's still an interesting saying because people don't actually know what I'm going to say. Behind every successful man, there's a surprise wife. Now, what's interesting about this saying is that I tried making it gender neutral. I tried saying behind every successful person, there's a surprised spouse. It's really hard to say surprised spouse, but it doesn't seem funny at all. And then you say, okay, behind every successful woman, there's a surprised man. And that just sounds really, really nasty. So it's interesting that gender symmetry is a complicated issue. In life, you need to take chances. Again, Ilan has said a little bit about this. In my old age, I took up backpacking, and here am I going over a pass in the Torres del Paine circuit in Patagonia. I am not doing email. I'm basically trying to look at the GPS to see how much further I have to go. I'm basically dying. It is very, very cold, as you can see, but I am so hot that I'm basically just can't take it. Now, maybe you shouldn't be too stupid. Ilan again mentioned the sea kayak story. The story is a little bit more interesting than he said. Basically, through collaborations with Sweden, there arose a Sweden-Stanford exchange program. Now, there's sort of a lack of symmetry here. Sweden is a country, Stanford is a university. And this program was designed so people from Sweden could come to Stanford in December, January, and February, for obvious reasons. And they obviously wouldn't want to go to New York, they wouldn't want to go to Berkeley, they wouldn't want to go to upstate California, they might have wanted to go to Los Angeles, but in any case, it was Stanford, Sweden. And after a while, we had lots of visitors coming, and we said, this is meant to be an exchange program. When are we going to get a chance to come to Sweden? So they decided to organize a conference. And I said, look, we've spent so much money on you guys coming to Stanford, why don't you organize a conference on the island, a villa, a sauna, all the good stuff. Instead, it was organized in Uppsala. And I guess in protest, I decided that I was going to spend the weekend before the meeting hiking on the islands. I'd never been to the archipelago before. One of my Swedish hiking friends who'd been at Stanford said, I'm sorry, you can't really hike on the islands. There are no hills, and you can't walk on water. He should have said yet, but he didn't. Anyway, so basically, I decided to use the link he provided, rent a sea kayak in Utto. On the plane over, it was actually a flash movie that I actually paid $5 for. That taught me how to sea kayak. One of the hardest things about sea kayaking is getting in and out of them. And I guess not dying when you turn over, but that part we didn't worry about. And again, I had a great sea kayak. I went from Utto to Ono. It was a total of about 30 kilometers. The unexpected thing, so the water is about 10 degrees centigrade, which is probably cold enough that you wouldn't be able to swim maybe more than half a mile before hypothermia set in. But what I didn't realize is that in the Swedish archipelago, the islands are completely empty until the weekend after midsummer. And I was there the weekend before midsummer. So in my day and a half of sea kayaking, I saw 2 sailing boats, 2 water taxis, and 1 Visby-class army destroyer. So there wasn't a lot of people around, but it was still amazing. Here's some pictures of the island that I slept on. I think I had a strange sense of security because I had a Swedish SIM card in my phone, and I had reception all the time. There's perfectly good SIM card reception on the islands. I forgot one thing that was really important. If you ever go hiking in Sweden in the summer, you need a face mask because tents don't get dark. Okay, but maybe it was stupid, I don't know. Anyway, to push it up, my advice to young, very clear, be passionate, do something you like doing. I always think of the situation where, let's say, your parents want you to become a doctor, and you don't really want to become a doctor, but you become a doctor, and you really are good at it, but you hate it. So now you've got to spend your whole life doing something that you actually don't like doing. So it's not a good idea to do anything that you wouldn't like to spend the rest of your life doing. Be persistent, don't give up. Be original. And this again might seem obvious, but basically if you hear somebody talk about something that sounds really cool, and you think you're going to copy them faster than they're going to do it, you're making a big mistake. You have to get your own angle onto it. You might be able to recast it in a certain way, but be original is a good idea. And finally, be kind and good. This sounds a little bit like, very soft. So I tell people that even if you aren't kind and good, act kind and good. Because basically you will disarm the opposition and you'll be able to do much, much better. Okay. I wanted to thank my towering heroes of science, Sinead Lifson, this group that you've already seen before. Basically, by the time I got to Cambridge, John Kendrew had left to found the EMBO lab in Heidelberg. Bob Diamond, I was his only PhD student. We had a very good relationship, although we actually never published a paper together. We ended up having papers in the same issue of the same journal in adjacent page numbers, but that's something which is going to be lost on people who get papers out of the thing. I've had an interesting group of people, about 2/3 postdocs, 1/3 PhD students, about 45 people. I want to thank the Nobel Committee now. Obviously wants to thank the Nobel Committee. They got him to give these ridiculous talks and dress up and so on. But actually, they did something very interesting. Firstly, and I think most importantly, they gave a Nobel Prize in computational science. Now, there had been Nobel Prizes in, say, computational chemistry that were very specific. This one was much more general. It was also for a method which really hasn't worked yet. I mean, it's not like we are routinely predicting drugs by molecular dynamics or folding proteins. It has promise. They also told me, and this gets back to the comment I think that Phil Bourne made right at the beginning, and that is that they said they wanted to get this out of the way so they could then start to give more recognition of computational areas in biology. And finally, I think this whole thing was somewhat tailored. This prize was given for multiscale models. Now, a Nobel Prize is meant to be for one thing. But by definition, multiscale models is for at least 2 or 3 things. So I think that in many, many ways, and they were actually so happy about this, they told me that in Swedish it's flerskalig, and it's a word that is hardly ever used in Swedish to mean multiscale. I must say it's a term that I'd never used until after this time. And then finally, well, my punchline is now being stolen by Ilan. Our field is the big winner, and I think we all agree with this. But about a week after the announcement at Stanford, I was asked to go out to the football field, the American football field at Stanford. It was the homecoming game with UCLA. All the alumni were there. And football is a big deal for Stanford. Stanford raises almost $1 billion a year in donations. So doing things like this for the alumni is a good thing. And I mean the football, not the Nobel Prizes. But basically, I think a Nobel laureate had never gone out in the field, and I'm with my eldest grandson here, and my wife is also in the picture. But basically, the announcer asked everyone to stand up, and they started to scream, Nobel Prize, Nobel Prize, and 50,000 people doing that is a high which makes everything seem very anticlimactic afterwards. Thank you all for your attention.
Questions? Think we'll...
Get me really drunk, I guess. Okay. Your question? How come I went on for such a long time?
So we will...
What do I do differently?
Can you speak to the mic?
You mean in general now? I would say as little as possible. So I remember very distinctly when this happened, I suddenly realized this is just nonsense, Somebody gives you something. But then I realized that when I was growing up, the celebrity scientists were incredibly important to me. And I'm sure they thought it was also a load of nonsense. And I suddenly realized that it's almost like a pyramid scheme or a chain ladder where you basically have to keep the interest in science by spending part of your time doing this. Now, I still like computer programming much, much more than giving talks like this. And, I'm getting too good at this, and that makes it even worse. Not computer programming, but giving talks. But I think I just do it for a small part of the time. I mean, I came here because I couldn't go to ISMB last year, and I promised Rafi I would come to 3D SIG, and I like to keep promises. That's actually, I used to break promises much, much more in the past. But somehow you kind of feel that you're a symbol of some kind. And that's an obligation. And otherwise, I don't know, I don't use it to get into restaurants, I don't use it to get theater tickets, I still fly economy, but I think it's a question of choice. I just somehow feel, and I dress like this when I give talks, so when I wear my t-shirt and shorts, no one recognizes me. So actually, that's just a way of getting anonymity.
Thank you to Michael for a great talk, and we will meet tomorrow morning. Thank you.